We are entering the era of general-purpose robots. Right now, diffusion policies are the state-of-the-art for teaching robots how to manipulate objects. They are incredibly powerful at modeling complex, multimodal human demonstrations. But they have a fatal flaw. They are brittle. If a robot encounters a minor deviation, a lighting change, or a slight object shift, it can easily slip into an out-of-distribution, or OOD, state. We call this a robustness blind spot. Once the policy enters this blind spot, its behavior is undefined, and task failure is practically guaranteed. Today, we are introducing REACH, Recovery Through Error-Aware Corrective Hindsight. It's a framework that gives diffusion policies something they've never had before: a built-in undo button and the ability to learn from their immediate mistakes using negative prompts. Here is exactly how it works. Before a robot can fix a mistake, it has to know it made one. Most systems wait until an object is dropped or a task is completely failed to register an error. REACH stops the error before the physical damage is done. We do this using an autoencoder-based Error Detector. We train a lightweight feed-forward autoencoder strictly on successful nominal execution images. It never sees a failed state during training. During real-time inference, the robot's cameras feed images into this autoencoder. If the robot is following a safe path, the autoencoder reconstructs the image perfectly, and the mean squared error is close to zero. But the moment the robot's arm drifts into an OOD state, an unseen angle, or a bad grasp, the reconstruction fails. The error spikes. By applying a statistical kappa sigma threshold, we trigger a safety fallback the millisecond this anomaly is detected. So, the alarm is triggered. What happens next? The robot retreats. Because diffusion policies output a sequence of planned actions, we maintain an execution buffer of the robot's recent history. In absolute action spaces, retreating is as simple as reversing the timeline of target coordinates. But in relative action spaces, like continuous 3D movement, we calculate the inverse transformations. We compute the exact reverse action sequence, ART, to safely roll the robot back to its last known safe SE3 pose. We are physically pulling the robot out of the blind spot. But retreating isn't enough. If we just ask the policy to try again from the same spot, it will likely repeat the exact same mistake. We need to tell the robot, don't do what you just did. This is where REACH introduces its core innovation: negative prompt guidance. If you've used AI image generators, you know what a negative prompt is. You tell the AI what not to draw. We applied this exact math to physical robot trajectories. We take the failed action sequence from our buffer and inject it into the diffusion model's reverse sampling process as a negative condition. Using an extended form of classifier-free guidance, the equation looks like this. The variable W is our guidance scale. By cranking up W, we mathematically repel the generated trajectory away from the negative condition. The robot dynamically generates a brand new action that still aims for the goal, but explicitly avoids the path that triggered the error. It's self-correction in real time without any task-specific retraining. To rigorously evaluate REACH, we set up a comprehensive testing ground. In simulation, we tackled environments like Push-T, RoboMimic, and MimicGen. For our real-world platform, we deployed an X-arm equipped with a multi-camera setup to handle the physical tasks. Our simulation suite covered everything from basic pushing to complex multi-stage assemblies. We wanted to see how the system handled different configurations, so we tested various error detector training datasets, like perfectly paired data versus proficient human data, across multiple guidance scales. The first big question: does the negative prompt actually steer the robot? The data says yes. When we measured the trajectory deviations, the prompted action, theta2, consistently showed a larger angle than the policy's natural variance, theta1. And as we increased the guidance scale, that steering effect grew even stronger, actively pushing the arm away from the failure zone. This active steering translates directly to higher success rates. Look at the CAN task. The baseline diffusion policy plateaued at a 60.1% success rate. But with REACH, Specifically, when pairing a proficient human error detector with an optimal guidance scale of 2.5, our success rate jumped to a massive 85%. The takeaways from these simulations are clear. Reach consistently beats the baseline. We learned that the quality of your error detector's training data significantly boosts your overall performance. However, tuning that guidance scale is critical. A moderate scale actively saves the trajectory, but cranking it too high can actually degrade it. To prove these massive simulation gains translate to the unpredictable real world, we deployed Reach directly onto a physical robotic arm. The results were definitive. Across complex, long-horizon tasks, the standard diffusion policy struggled. But when we activated Reach with the error detector, the success rates jumped drastically. We saw a 16% improvement in picking up cups, a 20% boost in the tricky banana and bowl task, and a solid 10% increase in high-precision brick stacking. We even pushed it to non-pick-and-place tasks like opening drawers, proving that the recovery behavior generalizes. Our ablation studies revealed two key insights. First, the error detector is the backbone. Simply adding prompt guidance isn't enough. The system must accurately know when it's out of distribution. Second, the guidance scale W has a sweet spot. Enough repulsion saves the task, but too much can push the robot into entirely new, unexplored errors. While Reach significantly boosts robustness, it is not perfect. Currently, our framework relies on environmental reversibility. If the robot knocks a glass off a table, rolling back its arm won't unbreak the glass. Our goal is to catch the error in the planning phase before physical contact is made. Additionally, a simple autoencoder has limited capacity in highly cluttered, dynamic visual scenes. Looking forward, the next step for Reach is integration with Vision Language Action, or VLA, models. Imagine replacing our pixel-based error detector with a vision transformer that outputs semantic negative prompts like, "Your grip is too far left." The diffusion policy would then process that language vector to correct its physical trajectory. Reach proves that we don't need perfect policies. We just need policies that know how to recover. By combining out-of-distribution detection with explicit negative prompting, we can make robotic agents vastly more reliable in the real world. Check out the full paper for the math, the architecture, and the complete dataset. Thanks for watching.